Okay. Good afternoon to all of you, dear course participants. I am delivering the lecture on remote sensing and GIS applications in soil resource management. In this lecture, I will discuss about the remote sensing of soils, how to map soil using conventional methods and digital technique, mapping of land degradation, watershed management, soil quality assessment, and finally soil carbon stock assessment. So these topics will be briefly covered in this lecture. So just giving a brief introduction to soil, for us or a soil scientist defined soil as it is a three-dimensional natural body. We call it is padon, and in picture you can see the area, length, width, and then depth perception. We can see here soils at various depth are different. Soil types are different in their physico-chemical characteristics. And if you see when we open a soil profile, we can see the various layers which we call it is soil horizon. Top horizon known as A horizon or agricultural horizon, agriculture activity we used to do. B is subsurface horizon and C is the parent material over which the soil has been formed or over which the soils has been deposited over that. So in a standard soil classification or soil studies, in general we study soil profile and up to 2 meter depth of the soils or the depth where we get the rock or hard material. If we see how the soil is formed from the compositions are, it is mineral matter, that is 45%, then organic matter, that is 5%, and air and water, that is 25%. So mainly the soils is forms of mineral matter that you are calling it is solid material, and this mineral matter is composed of sand, silt, and clay that are based on the size of the particles. And if you see the soil texture, generally this is the soil texture triangle where we can see there are 13 type of soil, 12 soil texture classes are there. When we go for the studying the soil using remote sensing, as I told you, one method is the conventional soil mapping where we used to study the standard soil. This is the standard soil mapping technique where we study the soil profiles and classify using soil taxonomy. So it is soil taxonomic label. We in general do the visual or digital analysis of satellite data. In general, that is the multispectral remote sensing data, where we identify and map soil landscape units. And then it is called as a qualitative analysis because soil using multispectral remote sensing data, we delineate the polygon of soil landscape units. Another technique is digital soil mapping techniques where we study surface soil properties. In case of degraded lands like erosion, salt affected soils, or any other degradation where the compactions, for example, surface soil properties changed, and that is that is reflected by its spectral characteristics, and therefore digital soil mapping we in general do for the mapping of soil properties, surface soil properties. We use the various techniques of geostatistic, hyperspectral remote sensing, and SVM, different statistical methods, where we study the uh, study the environmental covariables and soil properties, and we call it is quantitative analysis. If we see, there are three spectral regions which are we study using remote sensing data, and they are sensitive to the soil properties. So one is the visible wavelength, spectral region is visible near infrared region, which is 0.4 to 0.1 micrometer, and this is sensitive, or this is used for characterizing soil color, iron content and composition, soil water, organic matter. Near infrared and short wave infrared region, which is wavelength region of 1 to 2.5 micrometer, that is mainly used for characterizing phyllosilicates, or you can say the clay minerals, hydroxides, some sulfate salts, amphiboles, carbonates, organic matter of the soils. Then third spectral region is that mid-infrared region and thermal infrared region. Here this wavelength region is quite long, large, 2.5 to 25 micrometer, where the atmospheric window is available 3 to 5 and 8 to 14 micrometer. Other wavelength range in this wavelength region which is not transparent to the atmosphere, and this wavelength region, thermal infrared region, is mainly used for mapping of quartz, feldspars, silicate clay minerals, carbonates. So you can say this thermal bands is also useful for mapping of the clay minerals and carbonates. At present, if you see the hyperspectral remote sensing, or we are using up to 2.5 micrometer wavelength region, because up to that remote sensing data provide high spatial resolution, whereas in thermal infrared band spatial resolution of satellite data is coarse, and we are not getting a very significant spectral signature in thermal infrared band. At field level or laboratory level, that we can use, but at the remote sensing platform like your satellite or aerial satellite data, where we are not using much for mapping of soil properties using thermal infrared band. Just I show this is typical soil spectral signature spectrum of the soil, where you can see in case of soil wavelength, as they increase in wavelength region, there is an increase in the reflectance characteristics, and with increase here you are seeing some of the absorption peak. So this absorption peak is sensitive for the, for example, 1.4 and 1.9 micrometer. It is sensitive for the hygroscopic water. It also indicates about the clay minerals, but mainly clay is 2.1 micrometer. You can see the clay minerals. Organic matter you can say 2.4 or 2.3, and calcite minerals you can get in less than 2.5 micrometer. Here up to 0.5 to 0.7 you can see, you can use this wavelength region for mapping of iron oxide, and after that up to 1 micrometer or 1.4 micrometer you can say you can utilize for the organic matter mapping. So different component present in the soil, they are responsible for the reflectance reflectance of the soils, and distinct or definite wavelength region. If we observe in that wavelength region the reflectance or absorbance, we can use that to characterize individual soil components. So, if you make a spectral signature of the soil, that you can use to identify the minerals, organic matters, and salts. It is similar like that your signature, thumb impression, that is unique of each person. Similarly, different soils have a very unique spectral signature or spectral characteristics. We call it is spectral signature of soil. That we can study it using spectroscopy, where we record the reflected energy from the soil surface. And when energy is interacting with your soil, then you are finding two type of reflectance. One is the specular reflectance, means like a mirror, it is coming and going in another directions. And another is the diffuse reflectance. Diffuse reflectance is the most important reflectance, which is it is generated because of sufficient interaction of the soil matrix, means it's a composition of the soils. So we studied diffuse reflectance for characterizing or mapping individual soil composition or components. And this diffuse reflectance contains more information regarding the soil constituents. In general, if we want to study the spectral signature, we cannot generate using the multispectral remote sensing data, because in that the bands collecting the reflectance or absorbance in the broad wavelength region of 75 or 100 nanometer. But in case of hyperspectral remote sensing, you are collecting the reflectance in 10 nanometer wavelength region, 10 nanometer, or means very close. So you are able to generate a very continuous reflectance characteristics, or you can say you can generate like a spectral signature. In the graph you can see there of the different composition, water, carbonates, organic matter, quartz, clay minerals, you are getting a very distinct spectral reflectance and absorbance in various wavelength region. It is shown from 400 to 700, 500 nanometer. Visible wavelength, near infrared, and mid infrared. So here you can see the reflectance characteristics of the clay minerals. It is shown from 0.4 to 2.4 or 2.5 micrometer. You can see the different clay minerals have a very significant difference in their reflectance and their spectral change in the absorbance and reflectance. So all the constituents or compositions are giving you a very unique spectral characteristics that help you for the mapping of clay minerals, soil nutrients, organic carbon, salinity detection and mapping, soil texture, sand, clay mapping, like that one you can use for this. And here you notice that I have not written mapping of soil. It is mapping of individual soil properties or mapping of individual soil constituents. And these are based on the unique spectral signature. And today various hyperspectral remote sensing satellite data are available, which you can utilize. Here I have given one example of Hyperion 1 satellite, where it collects 220 spectral spectral bands from 0.3 to 2.5 micrometer with a 10 meter nano nanometer bandwidth. You can get a complete review of hyperspectral remote sensing application in soils in the referred literature. Now I will go for the conventional soil mapping. I just want to tell you that if you want a soil map, from where we can get. In India, several institute organizations exist. They provide the soil information or soil map. One is that National Bureau of Soil Survey and Land Use Planning, which has mapped the entire country at 1:250,000 scale using satellite data and published this soil map at 1:500,000 scale. This is available for the entire country. It is the small scale soil map. Another organization is Soil and Land Use Survey of India in New Delhi, which has also prepared the soil map of 50,000 to 50,000 scale, not continue for the entire country or for the entire state, but the catchment area, selected catchments. Every state also have the soil survey departments, all the states, and they also time to time used to generate the soil map. You can inquire from there. NRSC, ISRO, that also prepared the soil map at 1:50,000 scale, but not the entire country, but some of the area covered under NRIS project. So 1:50,000 scales, entire country is not covered. Only 36% of the total geographical area of the country has been mapped. Remaining are left. If you want global data, you want to see the global database of soil, World Soil Database map at 1:5 million scale is also available on the internet. So questions comes, when soil map is available, then why we want to learn soil mapping concept? Because I just want to inform why we want to map soils. You know the soil is a dynamic and its properties changes with the management. So the soil mapped in 250,000 by or any map if you are using, you just see that which year they have prepared. Generally we get the map prepared 20-30 years back. So those maps cannot will not reflect your the dynamic soil properties. For example, soil pH, soil organic carbon, salt concentration, those parameters, or nitrogen, phosphorus, potassium content in the soils, which is variable, which changes with time, that will not serve the purpose. Second, to know current status of soil properties, because the map are old, so we need the currents to study the current status. But the questions comes, where to take the soil samples if you want to prepare soil map, or if you want to study another kind of property, soil properties, then question comes, where to take the soil sample. So in this lecture I will explain you how to decide the sampling location, which method is there, which we generally using for soil mapping using remote sensing data. Then question comes, where to take soil sample, then what depth we should take the samples for soil quality assessment, soil health assessment, soil fertility, soil carbon stock assessment. In general, we go for collecting samples from 0 to 30 centimeter, 30 to 50 centimeter. So you need not to study the soil profile or pad-on. But if you want to study the soil genesis and complete soil analysis, then you have to study the soil profile. And so soil scientists, when they go for the conventional soil mapping, standard soil survey, they study the soil profile. Other planners or other researchers, can go for surface and subsurface sampling to characterize the soils for their to meet their objective. If you see the soils survey, three scales are there. We standard soil survey scale. Reconnaissance survey is done at 1:250,000 scales. Semi-detailed survey is done 1:50,000 scale, and detailed survey is done at 1:25,000 scales, and larger than that we call very detailed survey 1:10,000. We have various satellite or sensors available for the mapping of to meet the requirement of different scale. For example, larger scales you need Indian remote sensing satellite data list 4, IIRS list 4, or international satellite data ICONOS, QuickBird, or many others data are there. 1:50,000 you can use IIRS list 2, list 3, and 1:250,000 reconnaissance school you can use IIRS list 1, list 2, IIRS AWIF satellite data. So this scale is useful for village level planning. 25,000 scales is useful for block or tehsil level planning. 1:50,000 scales is useful for your district level planning, and 250,000 scales generally we use to for the state level planning or regional level planning. So just here you can see that suppose this is the land area, we call it is landscape. This landscape or land area, what is your total area, you can divide into the soil landscape unit or different polygons. How those polygons I can do, that I will explain in coming slides. We assume that is in that area the soils are same. So any one point we study the soil profile, we can say that is representing the entire subset. So if you see this one, you can see this is the one padon, and the padon is like this one, three-dimensional natural body, A layer, B layer, and C layer. And a group of padon is your polypadon. For padon is the basic soil characterizing unit, wrongly here written soil sampling unit. Padon is the basic soil taxonomic unit. Polypadon is the basic soil mapping unit. We can map polypadon, but we cannot map a single padon. Here soil, this analysis we call it is soil landscape model approach. In this approach, what we do, we delineate a land area which is similar in terms of the soil forming factors. The entire land we divide in such a way that the polygon should be similar in soil forming factors. If soil forming factors are same, then we say the soils are same. So because the soil mapping involve understanding of the soil forming factors, and you know the soil is formed by the 5 factors: climate, organism, relief, parent material, and time. These 5 factors are there. If two area, these factors are same, then both the places similar soil will develop. This is our assumption. And this we do through soil landscape analysis method, or also we call physiographic soil analysis approach. And the land area or polygon which we map, we call it is soil mapping unit. So what you do for any district or any area, if you are mapping, for simplicity I can say the climate and time, out of the 5 factors, climate and time may be the constant. You assume constant because entire area climate is same, and time time is, that is the pedologic time, or you can say weathering time. So that you can assume constant. Then only three factors are governing the soil formation in your area. So how we can get the polygon, how I can map? First you map the landform or geomorphology, that we are calling parent material. Then you map, further divide the landforms or geomorphology based on the topography, that is called relief factor, and then topography by, then it further divide based on the land use land cover, that is organism, and you will get the physiographic soil map unit. So this is the simple approach to get the soil map units, or to get the polygon, and the polygon will be similar in soil forming factors, and which polygons we call it is the physiographic units, and it is denoted as soil mapping units. So how we can do? Just I will explain with this satellite data. You see, this is the hill and this is the plain. So I have said is the SH Shivalik hills. This is the Shivalik hills in Dehradun, and this is the plain P, or this is the foothills, hills and foothills. So I have prepared the first parent material map. Two type of parent material is there. Then I have divided the parent materials further. Suppose this is the parent material hill. I have divided, then second level I have divided based on the slope. Here the slope is more, here the slope is less. So how we can see the slope more or less? You can see in the satellite data also that here is high drainage density and here is drainage density is low. So Survey of India topo sheet or digital elevation model we can use to see, that is the topography. And even satellite data also give you clue to study the topography. So I have divided this SH or Shivalik hills into two parts, upper and lower, and then I can say it is SH1, this is SH2. If you see the plain, this is the foothills, that is Piedmont plain, and lower after that you see the another division. We are saying the here the reflectance of this area is high, but here it is less, and basically this is the alluvial plain. So I can identify the various landform or geomorphology with the help of satellite data, and I can divide this one based on the topography, and third level I have to see the land use land cover. So soil changes largely because of the landform, followed by topography, then land use land cover. So you see in this satellite data, for your more simplicity, this is the remote sensing data where I want to prepare the soil mapping unit. This is the cropland, this is the cropland, this is the forest land, this is the hill. But you see, I have taken the digital elevation model of this DM. It is showing from here the 320 meter elevation or less. But here 883 higher elevation. So you can say this part is your higher elevation or hills is there. I can just divide hill and foothills, that is Piedmont plain. And this is the river going, and the material here you can say this is the deposited because of the river, so I call it is floodplain. This is young alluvial plain. And so you first prepare the parent material map, that is called geomorphology map or geology map. Now I will go for the second, to see the topography. How I can see the topography? I can see with the help of this DM also 3, 1, 2, 3 and 4 divisions I can see. And you can see also, if you see the drainage pattern from the topo sheet, so where two drainage are coming and meeting, it means there is a change in the slope. So that also give you idea for the slope, where the slope is breaking. So using that I can study the topography or slope classes. So each geomorphology is subdivided based on the topography or slope. So you see how hills and Piedmont plain I have divided into hills divided into H1 and H2. Here is also H2, means here this is hills H, this is also H2 hills, and both the places slope are same. That's why I have written as H2 H2. So it means H2 H2, if there and both the places the forest is there, so I can say the geomorphology, topography and land use are same. It means both the places soil will be same. So any one place I can study the soil and I can say about the other place the soil properties. That is the assumption. This is the principle of soil mapping. Here you can see the Piedmont plain was divided into upper Piedmont, middle Piedmont, lower middle and lower Piedmont, P4. 4 division based on the topography. Topographic informations I can derive with the help of Survey of India topo sheet, elevation map, drainage pattern and also seeing the satellite data. Now I further classified each geomorphology and slope based on the land use land cover. You see, this is the P2, this area entire P2 means lower Piedmont, middle Piedmont, but this middle Piedmont is here, this area is agriculture and this area is forest. So in this entire forest area P2F, entire is P2F. So anywhere I can take the samples and it will represent the entire P2F area. So if you go by like that interpretation, first you interpreted geomorphology, then geomorphology subdivide based on the topography, then it further subdivide based on the organism or land use land cover, then you will get a physiographic map. This physiographic map, this is the only based on the remote sensing data. I don't know about the soil unless I go there and study the soil. I study the soil profile, or if my interest is not soil profile, then I can take surface sample. If your objective is only to study the surface properties of soils, take surface samples. If you want surface and subsurface both, you can collect the soil sample. So here if you see the entire area, this area having similar soils, because entire area represent P4F, means lower Piedmont with forest cover, but this one is the lower Piedmont with agriculture, P4A. So this is the you can say the entire area the similar soils will be there. So any place you can take the soil samples where you can approach. Now I don't study the entire area, but I study only in the sample strip. I select one road which is corresponding to the entire my study area and going across our soil mapping units. So in map units it is crossing all map units, and we study only in the sample strips, not anywhere. We cannot take samples from anywhere because we cannot travel, we cannot go there. So we select this road and along the road both the sides, but not just near the road, 100 meters away from the 200 meter away from the road, you can take within 500 meter from the road samples where you can study the soil profiles. Here you can see the soil profiles locations has been shown to study, and you go to the field, characterize, take the samples, surface or subsurface. If you are interested for the profile study, you study the soil profile, and then you can get the soil, take the samples and analyze in the laboratory texture, pH, depth of the soils you can observe in the field, drainage of the soils we can study with the morphological properties of the soils, and this is the map unit H1F, H2F, what you have seen like that one, H1F, H2A, H2F. In this you have taken the soil samples. So those soil samples you analyze and you prepare a table like that one. So, and this map unit, it is an attribute table linked with your soil, physiographic map. Once you have studied the soil, then we call it is soil landscape or soil physiographic units and their soil characteristics. Like that you will able to prepare your soil map or soil characteristics as you required for your project area. So this is the physiographic soil map prepared for that at 1:50,000 scales. You can see that. So I can summarize at the end, that is you prepare first geomorphology, then divide based on the slope or relief, studying the topography. You take the then it be called geomorphology and slope, and then further you divide each map unit based on the land use, land cover. Remember that you cannot do entire three things at the same time. Then it will you will turn up preparing land use, land cover. You have to go by very systematic way, first mapping geomorphology, then combining topography with the geomorphology slope, and then geomorphology slope. Further unit will be divided based on the subdivided based on the land use, land cover. Then you will able to prepare a landscape map or physiographic map, and then you go for the study the soil or collect the soil in the various map units that will represent the entire polygon. So in the soil mapping there are three steps are there. First you do preliminary visual interpretation, then you do the ground truth collection. GT collection means go to the field, collect the soil samples or soil profiles, and third is your post field interpretation. Come to the office, analyze the soil's chemical physical properties, and then prepare the table showing that is map units and soil properties. Okay, so this is the way of very important part to study the soils, to map the soil, not the profile but where to take the soil samples to characterize the soil properties. Now third part, now you see we are having digital elevation model today, DEM, and it is very important or useful for soil resource assessment, and here you can see that is the use DEM for deriving various terrain attributes, elevation, slope, profile curvature, plan curvature, topographic indices, topographic wetness index, sediment transport index, stream power index. You can make from 3D, you can see you can generate 3D view of your terrain that help you for the studying the soil physiographic unit or landscape unit. You can see it if you are having in this way, then very easily you can map the that is your topographic information of the for physiographic analysis. Then second approach, which is today we are largely using, digital soil mapping approach. Digital soil mapping is the basically it is establishing the quantitative relationship between environmental data, means your terrain and spectral indices, and soil measurement or soil characteristics. So if you see here, ground truth soil data, you have collected the point samples, and each point samples you know the soil characteristics, for example organic carbon, pH, texture, depth, any properties of the soil. And you have for that your area from remote sensing data and digital elevation model, you can generate various maps. For example, terrain parameters map, vegetation spectral indices, several indices are there, soil spectral indices, climatic indices, climate data based indices. You can collect or you can generate 10, 25 or 50 maps which we call it is environmental covariates. Then you make the relationship, mathematical relationship between these two, and you can use for preparing digital soil map. So digital soil map is a rapid, it is a very fast techniques for mapping soil properties. But one thing I want to remember you that it is not the replacement of conventional soil mapping. Here digital soil mapping, you are making the relationship of soil surface properties using some statistical advanced models. For example, geostatistical, machine learning, in machine learning various algorithms are there, random forest, ANN, decision tree, which use by correlating this one you are preparing soil properties map that is known as a digital soil map. Here in a conventional soil mapping, I told you the soil is the form, soil is a function of 5 factors: climate, organism, relief, parent material and time. Here for the digital soil mapping, McBratney in 2003 given this equations. Soil is the function of S, and climate, organism, relief, parent material and time. These are the same but two are different, S and N. N is your GPS location, relative spatial position. N is GPS location of the point where you have collected the soil data, and S is the soil legacy data, or from previous map, prior knowledge of soil. If you are having any information of its properties, then that also we can use. And F is the function. How we can relate this one? It is the using this decision tree, random forest or neural network, advanced statistical methods. So in digital soil mapping, you can say it is simply the establishing spatial relationship between the soil sampling points and environmental covariates using various methods, and methods are geostatistic, multiple linear regression, machine learning method. Those methods are being used today to make the relationship between the soil properties of the point data and for the same area you have generated the environmental covariates, and you can prepare the digital soil map. Here you see we have prepared the digital soil nutrients mapping. It is digital elevation model, DM, Cartodem, prepared the slope map. Also prepared these maps, TWI, STI and SPI. Here in the watershed, in the entire area, I have taken the grid soil sampling at a regular interval. Soil samples were collected and analyzed for carbon, nitrogen and phosphorus, and then I made the relationship, correlation and regression analysis using terrain indices and soil attributes, and also did the geostatistical analysis, kriging and co-kriging, and then you can prepare the spatial distributed organic carbon, nitrogen and phosphorus map. So this individual nutrient map can be generated, and which you can use for your precision agriculture or fertilizer management, nutrient management. Now that was the part of soil mapping. Now I tell about some land degradation, how we can map degraded lands. You know the land degradation in our country, total area is 120 million hectare is a total area, And cropland is having 104 million hectare. Cropland is affected by various land degradation, and out of that, water erosion is the causing the major land degradation, water erosion. And water and wind erosion both together are making around 85 million hectares, or you can say that 81 or 82% of our land degradation is because of erosion. Physical degradation, that is salt affected soils, and chemical degradation, which you mean by salt affected development of salt affected soils, physical degradation, and so like that in agriculture area, arable lands. If you see, the one major use is their watershed management. You have heard that one. What do we mean by watershed? Or here you can come here before that. Soil, how we can map the soil erosion? You say here in this satellite data, there is a lot of dissection. Soil erosion are four types: sheet erosion, sheet and rill erosion, gully erosion, dense gully erosion. Here you can see that is the gully erosion, very severe erosion, because you are seeing lot of gullies or drainage lines, dissected land. This is the moderate erosion, that is gully erosion. Also you are seeing gully, but here gully intensity is very high. So by seeing these features on the remote sensing data, FCC, we can characterize the area under sheet erosion or slight erosion, moderate erosion, and severe erosion. If you see in the field, the sheet erosion occurs like that one, surface soil is washed out. So here if you see, the surface area has been washed out, so sand and sand particles are left, and even organic matter has been washed out, so you are getting high reflectance. So it is characterized as a sheet and rill erosion. We use some erosion models also for mapping of erosion. Here you can see the most important erosion model widely used in the world is Russell model. We call it is revised universal soil loss equation. In this we use the climate data, soil map, topography, and land use land cover. So topography informations we get from DM. We can prepare slope length and slope steepness factors, 2 factors. And here from land use land cover map, you can generate the C vegetation cover and management practices. Soil map, you can get the soil erodibility map you can generate, and climate data, I can generate rainfall erosivity map. If you integrate these maps, these factors, then we get the soil erosion risk area. Here you see how this model is implemented. From DM we have generated LS factor. From satellite data we generated the land use land cover and slope and soil erodibility factors. Integrating that one, we get the soil erosion map. And here in various land use land cover, you can also calculate the soil erosion rate. So soil erosion rate can be studied with that one. Another is the salt affected soils and waterlogged area. Here in this is the FCC. Salt affected soils, what happens? Soils accumulates neutral soluble salts on the surface. This is the salts in the field photograph. It gives high reflectance. That's why it appears on the standard FCC as a white tone. And waterlogged area, it appears as a blue tone, or slightly moist area or surface moist area, surface water logging, you can see that is the bluish tone. This can be mapped easily with your remote sensing data, because in degraded lands, surface properties of the soils are changed, and that can be directly affect the reflectance characteristics of the soil. Here one example is given. This is the Rohtak district of Haryana, and in the FCC you can see white tone. These all are salt affected soils. We mapped in 2000. These are the salt affected soils where you are seeing the yellow color. This is the salt affected soils based on the supervised classification. Here I have shown in 2000 this was the salt affected soils, but it was mapped when I saw in 1990, 10 years before, the yellow color is showing here the salt affected soils, and this area you are not getting any salt affected soils. But after 10 years you are getting here the salt affected soils. So there is a increase in salt affected soils after 10 years. So you can study the change detection, or you can monitor your resources, that is increase or decrease of salt affected soils, how much and in which direction or in which part of the area. Another application in soil resource assessment is, in general today we want to study the climate change, and in that case carbon content, estimating the carbon stock becomes very important. And one thing I want to tell you, that soil is a major sink of the carbon present on the earth's surface. If you see soil, 1 meter depth of the soil in the global level, it stored 1500 petagram of carbon, where the atmosphere is having carbon of 750 petagram, and vegetation, whatever the vegetation on the earth's surface is there, they total have only 560 petagram of carbon global level. So you can say the soil having 3 times higher, more carbon stock in the soil. So soil, you can see this is the soil profile of the forest area, and the top layer you see the dark color, it is because of organic matter. Even organic matter, organic carbon present also in this area. So soil is a major sink of the carbon, and if this carbon released to the atmosphere, then it may cause another problem of global warming. That's why soil should not be exposed to the atmosphere, otherwise it will release the carbon to the atmosphere. Then question comes that can we estimate the stock of the carbon in the soils? So soil carbon stock can be estimated, how much stock is there. It can be estimated by area of the map units, the soil map units, and the carbon density, SOC density in that map unit. And SOC density you can calculate using this equation, where Qi is the carbon density, soil organic carbon density, C is your soil carbon content, so carbon analysis we can do, soil organic carbon, D bulk density, E soil depth, and G is your fraction, coarse volume fraction of coarse elements, means stones or that is gravels, how much volume of that one. We have to subtract that one because they don't contain organic carbon. So using this formula we can use the soil carbon density, and then you multiply with area, you will get the soil carbon stock. Here you can see soil carbon stock we mapped for the entire country in our national project, which has been published, the paper in this one you can study. we have taken the soil sample, this is the sampling points, around 2000 samples we have taken in the entire country, and using the your machine learning techniques, we map the distribution of organic carbon and inorganic carbon. How much stock is there? We found that 22.7 petagram of carbon, soil organic carbon, and 12.8 petagram of inorganic carbon are present in Indian soils. Higher carbon density we found in plantation crops, followed by forest and then agriculture land. Agriculture land carbon density is less. So forest soils have higher soil carbon stock of 9.38 petagram present in the soils, and this is the soil carbon stock distribution in the country. So you can go through this paper. We can also use how in the future carbon will decrease or carbon will reduce in our soils. So here we use the century model to simulate from 2011 to 2099 or 21st century, or at the end of 21st 20 in year of 2099, we found that is the organic carbon is going to decrease regularly, and from 5490 to it will reduce to the 4793. So we predicted that is the in all the soils of Himalaya. We have done one study in the Himalaya, mid Himalaya in Tehri Garhwal, where we found that is this has been reducing, it will reduce continuously, will cause decrease in organic carbon. Another is the soil quality, which is the important. Today we want to study the quality of the soils. So soil quality we cannot measure directly. So only we use to assess with the help of indicators. And for indicators are physical properties, chemical properties, and biological properties. These are the bulk density, drainage, soil texture, depth. These are the physical properties. pH, EC, organic carbon, base saturation, cation exchange capacity are the chemical properties. And biological properties, earthworms, respiration, microbial biomass. So using these properties, we can assess the soil quality. We cannot measure soil quality because soil quality is a complex properties which cannot be measured with any instrument or cannot be measured directly. It is a complex, or it is a proper. It can be assessed with the help of various properties of physical, chemical, and biological properties. So here I have showing you one soil quality, soil health and soil quality assessment in one watershed. You see, be prepared by taking the soil samples at regular grid interval, prepared by statistical method kriging, organic carbon, phosphorus, and here is the total nitrogen, and then we have generated the soil quality index map, and it is showing that is the red colors having high soil quality index. So here your crop performance will be very high, and this is the lowest soil quality index. So we can map spatial soil quality map, and where soil quality, we use this formula, soil quality index is the function of properties. What are the R is the properties of the soils, and W is the weightage, what weightage we have given to that one. So one part is left, that is we can go for the we also use remote sensing data in watershed management. What do we mean by watershed? We say the watershed is a natural drainage area which contribute runoff to a common outlet. Means this is a, suppose drainage line are there, and water from the entire area get released from the outlet. So this is one watershed. If you want to manage the natural resources very efficiently, then we do the watershed management. And watershed is a natural hydrologic unit, or it is also known as a natural unit of resource management. So in this area, in watershed, we used to study land use cover, forest cover, soil, topography, geology, climate, and village area. So by this one we can assess these resources, and we can go for optimal utilization of these natural resources for efficient, sustainable way. So watershed management is we do for the sustainable agriculture. And in India, integrated watershed management program being run in the entire country in various states, and the major purpose is to restore the ecological balance by harnessing and conservation of degraded natural resources such as vegetation cover and water. So how we can do with the remote sensing data? Suppose this is one watershed in the Jhabua district of Madhya Pradesh. We prepared the land use land cover. This is the land with scrub land, Kharif and Rabi. Soil map, prepared the slope map, hydrogeomorphology map, and all these maps informations are integrated and generated the action plan for its optimal utilization of resources for and we suggested that is this green area go for agroforestry. This area go for intensive agriculture, and this yellow color is showing that there you go for double crop agriculture. So by using this one, remote sensing data can be used for preparing watershed management plan, so that you can conserve your resources and prepare and increase your crop yield and restore your soil and water for the future. So I can conclude that remote sensing satellite data can be used to derive reliable information of soil and land resources, which is very much required for the planning of natural resources. And this remote sensing data and GIS, both tools, are important for generating spatial information of soil resources, evaluation of their potential, and mapping of degraded lands for land use planning. And in a climate change studies or in future climate, global warming, soil, as I told, soil is having a sink of the carbon, so you can assess the carbon stock of your soils and various soils, and that is important for your soil quality, maintaining soil quality, and improving your climate change its stress also in future. Thank you very much.